Hi, in this video, I'll be going through more about ring theory, and in particular, we'll be going through the isomorphism theorems for rings, which you'll see is very similar to the isomorphism theorems for groups. And so, to define what a ring homomorphism is, we do it the natural way, and we say that it must first be a group homomorphism, and then it also must respect multiplication. So phi of A times B must equal to phi of A times phi of B. And the kernel of a ring homomorphism is defined to be the set that maps to 0. So you can see in this case it's not mapped to 1, but mapped to the additive identity. And a bijective ring homomorphism is then known as an isomorphism. And we can say this is because an inverse of a ring homomorphism is also a ring homomorphism. So then we can now define it to be bijective. It's called a isomorphism. And so some examples is over here, and we can see that when we map z to the z over nz, and the kernel is nz, so this is a quotient map. We have some other ring homomorphisms such as the embedding. And now let's prove some propositions about ring homomorphism. Is that the image is a subring and the kernel is also a subring of R. And so for the first one, we just take two elements in the image. And so S1 must equals to phi of R1 and S2 equals to phi of R2 for some R1 and R2 in R. Then we take phi of R1 minus R2 and we see there is just S1 minus S2. Because it's a ring homomorphism. Similarly for multiplication. And this show both of them will still be in the image. So it's closed under subtraction and under multiplication, and we are done. For number 2, to show that a kernel is a subring, then we just need to check that the elements is closed under multiplication and subtraction as well. And so you just do the easy verification and you can check essentially that it is true. And then we will also have for any R, we have alpha R, phi of R alpha equals to phi of R times phi of alpha. And so this means that R alpha, comma alpha R will be in the kernel. So you can see what property you want is that when you have a kernel, then alpha is an element, and you have an alpha element of a kernel, it is closed under multiplication by all elements in R, which is the bigger set. So you got R is here, and we got the kernel is here. And the kernel is a subring, so it's closed under its own multiplication. But not only that, the kernel is closed under multiplication by all the elements in R. So this property is something that we can utilize to define a kernel. And really, that is saying this. We say that R times a subset of R. So R is an element in big R. It will be defined as like a coset. And you can define the right multiplication one as well. And then we call this property an ideal. And so I must be a subring of R. And this I is closed under net multiplication by elements from R. So what it means is R, little r times capital I is a subset of big I. And a right ideal is the similar, but now it's closed under right multiplication. And the subset capital I will be known as an ideal if it's a two-sided ideal, meaning it's both a left ideal and a right ideal. And so with this property now, you're able to define the quotient group to be a ring under the binary operation, addition and multiplication respectively. And this operation will be well defined now. So it is analogous to saying in group theory where you have a normal group. So you need certain properties of the normal group so that you can define a quotient group. And with this, we found out that mathematicians discovered that the property that you really want is this ideal property where you're close under multiplication by elements in R. And so when you have that, then you can really define a quotient group to be well defined. So there won't be any overlaps in the case over here, where you get sent to different elements for the different representative in your ideal. And then for any of the subgroups such that the above operations can be well defined is actually an ideal. So it's two ways. So when I is an ideal of R, then the ring is known as the quotient ring. And with that, we can now state the isomorphism theorems that if phi is a ring homomorphism, the kernel will be an ideal, the image is a subring, and R quotient out the kernel is just isomorphic to the image. And so the proof of this follows as what we already know is that we already have an isomorphism from group theory. So this isomorphism, you just need to check that it's also a multiplicative one. So I'll leave it to you to check how we define the isomorphism in group theory. And what you really want to now say is, because you have the properties of the ring, you can just check that the ring properties are also respected with this same isomorphism. So it's an easy verification, and once you check that, you can actually just see that R quotient of the kernel is just isomorphic to the phi of R in rings as a ring. So multiplication here is preserved. So that's the first isomorphism theorem, and now you can see the similarities between this and the group theory one. For the second isomorphism theorem, if I is an ideal of R, then the map from R to the quotient group is surjective with the kernel of I. And so every ideal is a kernel of some ring homomorphism. And really, it's just saying if I is any ideal, then the quotient is a ring. And so you can form a map from R to R plus I, which is now a group homomorphism with the kernel I. And then you just check that this phi is a ring homomorphism. And so you now shown that for any ideal, you can define a ring homomorphism with its kernel as the ideal. So thus a kernel is an ideal is the kernel of any ring homomorphism. And so some examples of what we are going through is some examples of the ideals will be R and 0 will of course be the ideals. And we say if I is proper if I don't equals to R. So of course I must be a proper subset of R. And the 0 ring is always the trivial ideal. And you can verify that the multiples of n is an ideal of the positive integers. And these are the only ideals of Z. And really, why are they the only ideals is because they are firstly the only subgroups. So that's the first criterion already. And then you just need to check the properties whole. And so the projection from Z to the remainders is known as the reduction modulo map. And this is very important because by having a ring homomorphism, we see that it allows us to solve questions in number theory, known as the Delphin equations. And really, when you study more about integers and stuff in number theory, you realize how this reduction homomorphism comes into play. And one thing, let's say, we want to observe is that the equation is a relation between elements in the Z. But because you have a ring homomorphism between Z and the remainders, you can now say that this relation must also hold in the homomorphism in the remainder side. So you just need to imagine you take this whole equation and you mod n with it. So for example, if n equals to 4, then the squares of mod 4 are just 0 and 1. And so this is just 0 and 1, this is 0 and 1, and this is 0 and 3. And so you really can't form in any way a set of solutions to this equation. And because you can't form any solutions here, you can't form any solutions in the original. So you actually prove that the original equation has no integer solutions. So I hope you find that interesting and you can read more about it. Next, we want to show the second isomorphism theorems for rings, and it's really saying that A plus B quotient of B is isomorphic to A quotient of A intersect B as a ring. And what you really need to do is you already have this from group theory isomorphism and just check ring properties. So the proof for the rest of the isomorphism theorems look exactly like the group one. So I'll leave it to you to go watch my group video. And what you really need to practice on is just checking that it has the rings, it respects ring operation of multiplication as well. So I'll now show you examples of me doing problems to let you familiarize yourself with solving questions related to ideals and homomorphisms. And for the first one, we will prove that this set over here with this condition is a right ideal, and the other one is the left ideal, and they are known as the right and left annihilators of A respectively. So it's easy to check because you just need to first take any element in R and any element in this set I, we call it, and then we just verify that when you take x times R, this is some element in the right ideal, and then you just verify that it is contained in the ideal. So you just take A times this, then well AX is 0, so 0 times R is 0, so I of times capital I times little r is a subset of I, so it's the right ideal. And then you can verify, so for the left annihilator as well, it's the same. And then we can prove that if L is a left ideal, then this set here is a two-sided ideal. And really it's because if you take x to be an element of this, then x times r bracket A must equals to x times RA. But because L is a left ideal, RA will be an element of L. And being an element of L, when you multiply with any element from the, so L is a left ideal, so RA being an element of L, then you take R, you multiply with A, will still be an element of L. And since x times A for all elements in L equals to 0, this A can now be replaced with RA, and so x times RA is 0, and so XR is an element of the following group, the following ring, and we are done. And now let's do another question, and it states that if phi is a ring homomorphism, and this ring homomorphism doesn't send the identity to the identity, then it must send it to a zero divisor. And it's simple to see why. Because if it's not equals to 1, then it must equals to some other element S. And so, when you take the ring of 1 minus 1 times 1, it must equals to 1 over here. So, it's just the phi of 1 times the phi of 1, which equals to S squared. And here is just phi of 1, which equals to S. So, S squared equals to S. And this just means that S, so you bring over here, you use the distributive law, S bracket S minus 1 equals to 0. And since S don't equals to 1, S minus 1 don't equals to 0. So S is a 0 divisor. And I'll leave it to you to now deduce. So now we want to deduce that S is an integral domain for every ring homomorphism that sends identity to identity. And that's because if it sends the identity to identity, you can now play around with it and then you just multiply it to see that it won't have any zero divisors. And so it must be if S is an integral domain, then it must send the identity to the identity. And I'll leave it to you to verify B, as it's a very straightforward verification. Let me know in the comments down below if you have any help. This is all for this video. I'll see you again. Bye.